This is my periodic table of elements that shows all of the requirements from topic 3. I'll go over all of them in this presentation. So first off, the different elements. So these two groups that are highlighted in green are the S block, including helium up here as well. This whole group right here is the P block. It's highlighted in blue. This right here, groups 3 to 12, are the D block, and at the bottom, the lanthanoids and the actinoids make up the F block. The groups on the periodic table are located at the top of every column. They represent the number of valence electrons presented in each atom. So when you get to 13 and on, you take the last digit of the number, and that tells you how many valence electrons are in the atoms presented under the column. And IUPAC says that you list the atoms, you list the group numbers 1 to 18, and you don't include the lanthanoids and the actinoids. The similarities and differences between the different groups, which are each separate columns, are represented by their different trends. So they might both be in the same group. They might both be in the same group, but they differ where they stand. So like here in group 18, at the bottom, this element is a metal, but at the top, helium is a non-metal. So they're both in the same group, but they consist of different properties. But for here, these two elements, they're both non-metals, and they're in the same group. So that's the similarity they both have within each other. The periods on the table are on this side right here, and they're listed 1 to 7. And these numbers tell us that the number of energy levels each atom has. So for period number 1, each of those elements have 1 electron shell. And now we'll talk about the metals and non-metals. So I designated which was a metal and which was not a non-metal and which was a metalloid by these little dots that you see inside of the periodic table. If it's a gray looking dot, then it's a metal. If it's a red looking dot, it's a non-metal. And if it's a green dot, it's a metalloid. And metals are found on the left side of the stair-stepping block, the stair-stepping block is the list of metalloids. So from here all the way over, all of those consist of metals except for hydrogen, which is a non-metal. And all the non-metals are on the right side of the stair-stepping block, which include helium and all of these down here until you get here, and hydrogen. And all the metalloids are the stair-stepping block, which consists of 7 elements on the periodic table. Properties of each. So the metals are shiny, solid, ductile and malleable, and and they're good conductors of heat and electricity. And nonmetals are the complete opposite of metals, which include being brittle, not malleable, or ductile. They're poor conductors of heat and electricity, and they tend to gain electrons in chemical reactions. Metalloids, they adapt properties of both metals and nonmetals depending on where they are in the locate. And next I'll talk about the location of alkali metals, transition metals, halogens, noble gases, and lanthanoids and actinoids. Alkali metals are found in group 1, so this entire group is alkali metals. Transition metals are found in groups 3 to 12, all of the D block pretty much. Noble gases are group 18, which is this N block right here. And halogens are found in group 17, which is to the left of the noble gases. And lanthanoids and actinoids are both on the bottom. Lanthanoids is the top row, and actinoids are the bottom row. And now I'll tell you about the trends. So I designated the different trends based on the arrows on the bottom that showed what the group trend has, and on the side that shows the period trend. The atomic radius trend is on the bottom here, and it says that you increase when you go from right to left in terms of the atomic radius, and when you go down a column, you increase your atomic radius. And this is because you either increase the number of protons and electrons across a period, and also because of electron shielding. And atomic radius is basically the atoms, 1/2 of the atom's distance from the nuclei. So like a circle, it'd be half of it. So it's the same as the atomic radii. The ionic radius is very similar to the atomic radius, but ionic radius is the radius of one's ion. And the ionic radius acts just like the atomic radius because they're together. And the ionic radius also increases from right to left across a period, and increases going down a period. Yeah, and this is because of either additional layers of electrons or atomic orbitals. And next is ionization energy, which measures the energy required to remove an electron from a neutral atom in its gaseous state. So ionization energy, which is on the top, increases from left to right, going across a period, and increases up a group. And this is because the valence electrons, either the valence electrons stability or electron shielding, and after that the electron affinity, which is an atom's ability to accept an electron. And it also is just like it's just like ionization energy, which increases from left to right and increases up a group, and that's because of the decrease in atomic radius and increase in atomic radius going from either up the group or across the period. Electronegativity is also just like the last two. It increases from left to right and increases up a period, which is on the side right there. That's because the atomic radius increases down the group, or because of the amount of valence electrons present in an atom. And electronegativity describes an atom's ability to attract electrons. And I didn't say this before, but the group numbers up here, IUPAC. Never mind. And the trends in metallic and non-metallic behavior, you just have to find where the metals and non-metals are, which are already designated. So based on what I just said about the different trends, you'd find one. So like, for example, I used francium and fluorine over here. So francium is a metal, and it has is one of the least electronegative because it's on this side when electronegativity increases down a period. And also metals tend to form cations because they have lower ionization energies, which would also fit francium because it's at the bottom when they increase down, and the atomic size is at its biggest because atomic radius goes the opposite direction of the electronegativity and ionization. And they form basic oxides, which you wouldn't be able to tell based on the periodic table, but they do. And the outer shell moves farther away. When you're talking about nonmetals, I chose fluorine, which is at the top under group 17. Fluorine is the most electronegative, and they tend to form anions based on where they are on the periodic table. They form acid oxides. They have higher ionization energy because it increases down a period. And they have higher negatives. But they have lower atomic sizes because atomic radius increases down from right to left, not left to right. And ionization depends on differences in electronegatives, which you'd have to do math for that, but it does. And on the back of my periodic table, I made